All right, we're going to be exploring working with cylinders. Specifically, we're going to try to understand the variables related to cans and how it relates to the surface area, so that is the materials required to make a can, and the volume, that is the amount of stuff that the can can hold. So here's how the problem presents itself. We have, let's suppose there's a fixed surface area. So let's say it's like a Red Bull can or a tuna fish can or something like that. So there's a specific amount of material required to make that can. Now, that can, as it exists, holds a certain amount of stuff. And what we're interested in is that can holding the most amount of stuff possible? In other words, is that can optimized? Is it holding everything that it could possibly hold? So, the can has an existing volume, but what we're going to do is imagine melting down all the materials and cutting out a new can that's going to have a different height, and it's going to have a different radius, and could potentially hold more volume than the can already holds currently. So in other words, we are trying to maximize the volume of the can. Here's how the problem comes in. First of all, when I look at my volume, the volume is a function of the radius and the height. There's nothing in the volume about surface area. So what we have to do is try to see if there's a way to connect the surface area to the volume. The other thing we need to do is to try to find a way to write volume so that it only has one variable, not two other variables, determining its value. So the first thing we need to do is to understand what happens when you have a fixed surface area. Here we can see that, again, I fixed the surface area at a hypothetical 300 square centimeters. And what I learn is, or just by visualizing it, if I have a fixed amount of materials, if I make a really short can, there's going to be a lot of materials left over to make the circle top and the circle bottom. However, if I make a really tall can, there's not going to be very much material left to make the top and bottom circles. So what we learn is the height and the radius are what I call codependent. That is to say, if I make a change in the height, that affects the radius directly because of the fixed amount of surface area that we have. Specifically, the dependency relationship between height and radius is an inverse proportion. That is to say, as height goes down, radius goes up, and vice versa. So that's just trying to understand why I'm going to do what I'm going to do and trying to understand this particular problem. So since the area is fixed, that is a way to tie together the radius and the height so that they're bound together forever. Specifically, the area of a can, a cylinder, is expressed as 2 times pi r squared. That's 2 times the area of the circle, top and bottom, plus 2 pi r h, 2 pi r representing the length, h representing the height of this rectangle, and the height of the can. And then, since the area is fixed, we have 300. Now we can see that r and h exist within the same equation, so all I have to do is solve the equation for h. So the first thing I do is I subtract 2 pi r squared from both sides. So basically I subtracted it, it came over to this side of the equation. Then I'm going to divide both sides by 2 pi r, producing this value for h. So once again, we can see this height-radius codependency in very specific form, and that is, if I know the radius, I put that here and here, do some number crunching, and that will force the height to be whatever is left over. So this is the magic key that unlocks the volume, so that instead of having volume as a function of radius and height, we can have a volume a function of height all by itself, or sorry, radius all by itself. Notice, by the way, the fixed surface area of 300 is now manifest itself into the equation right here. All of this stuff is because of the fixed surface area of 300. Now just a little bit of mathematical cosmetics, and I could clean this whole thing up, and it looks really nice. It's just a straight-up cubic polynomial, 150r minus pi r cubed. The rest of the work is straight-up calculus. So here all we have to do is take the derivative of this, so it's 150 minus 3 pi r squared. Then we set the derivative equal to 0. We add 3 pi r squared to both sides, divide by 3 pi, take the square to both sides, keep only the positive one, and we determine by putting this volume into this equation that if we use 50 over pi square root as our radius, we put that in, we can calculate a volume of 398.9 cubic centimeters, same as milliliters. So the largest amount that a 300 square centimeter surface area can contain is 3,990 or almost 400 milliliters. That's our conclusion. So most important part of this whole experience is understanding how we can take a fixed surface area so that we can make a connection between radius and height. We use the connection between radius and height to eliminate one of the variables in my volume formula so that we can then apply calculus methods to it. I hope you find this helpful. Thanks for watching.